Hi everyone, my name is Łukasz Paszkowski. I'm a software team leader at Stila. Today I'm going to talk on enhancing internode compression, during which we walk through a customer issue that led to improvements. You will learn about the problem we faced, the steps taken to resolve it, and gain valuable insight into compression techniques. My background is in mathematics. I spent most of my time working for research institutions where I managed to start a PACE2 project that led to medtech company and clinical trials. After working hours, I'm a big fan of other activities. One day in 2023, a customer raised concerns about unexpectedly high networking costs associated with using Stila, particularly related to interzone replication. Upon investigating the issue, users examined Wireshark captures and observed some unusual patterns. They found out that data that should have been compressed often appeared as a plain text. Moreover, the compression seemed inefficient as the size reduction was only about 25% at best. This led them to believe that the compression feature might not be functioning properly. At the time the customer issue occurred, whenever internode compression was activated, the RPC traffic was being compressed using the LZ4 algorithm. LZ4, as the name implies, is based on the length-ziv compression technique and performs dictionary coding without an entropy coding step, which explains why a plain text can appear in a compressed data blocks. One might question why LZ4 was selected for network compression instead of a more advanced tool like ZSTD, which offers better compression ratios. The answer lies in the history of the systems involved. Stila, being an offshoot of Cassandra, inherited this decision, as at the time LZ4 was selected, ZSTD had not yet been developed. Later on, however, when Cassandra was questioned about why LZ4 was preferred, their explanation was that the overall time required to compress, transmit the compressed data, and decompress it using ZSTD was longer than transmitting data without compression. While this reasoning might still hold in today's high bandwidth network, it does not account for situations where network cost could outweigh CPU costs. So what is the compression all about? Compression is a process of reducing size of data files in order to save space for transmission time. It works by encoding information efficiently. Mathematically speaking, for a given set of messages, to design an encoding which minimizes the expected size after the encoding. In practice, to have shorter codes for more likely messages. In the information theory, an entropy coding is a lossless data compression method that attempts to approach the lowest bound declared by Shannon's source coding theorem, which states that any lossless data compression method must have an expected code length greater than or equal to the entropy of the source. Entropy coding operates on an abstract level, such that it can operate on any set of symbols as long as we have information about the probabilities of each symbol. For example, consider a message consisting of 4 characters, A, B, C, and D, with respective probabilities, a half, a quarter, and 1/8. The table demonstrates possible encodings of these letters. For the naive encoding, we clearly need more than 1 bit to encode 4 letters. Hence, it uses 2 bits per symbol. Note that this approach does not take the probabilities into account. it's inefficient. The more symbols we have, the more bits are required to encode one symbol. So instead of using bit strings of fixed size, the same symbols can be encoded with bit strings of varying length, where more frequent symbols are assigned to shorter codes. From our optimal encoding, we can easily decode the original symbol. When the first bit is 0, the symbol is A. Otherwise, it's B, C, or D, and the second and the third bit determine which one is it. Such variable length codes can be readily constructed when the probabilities are negative powers of 2. This is a classic approach known as Huffman coding. However, when the probabilities are arbitrary, then Huffman coding is no longer applicable without approximations of probabilities, which makes the coding suboptimal. Dictionary coding is a class of lossless data compression techniques that operate on searching for matches between the text to be compressed and a set of strings contained in a data structure called a dictionary maintained by the encoder. When the encoder finds a match, it substitutes a reference to the string's position in the data structure. So how does the dictionary coding work? The first step is to create a dictionary that maps each unique value in a dataset to a corresponding code. The original dataset is then transformed by replacing each occurrence of a value with its corresponding code from the dictionary. This results in a much smaller data footprint, as repeated values are encoded as short, fixed-length codes. Both the dictionary and the encoded data are stored together. When accessing the data, the encoded values can be quickly translated back to the original form using the dictionary. This way, our 8-bit ASCII phrase that takes 38 bytes can be compressed to a message that has a total of 33 bits. This is a significant saving. Of course, the real saving would be lower, as the dictionary itself has to be transmitted alongside with the message. Note, however, that as the message being transmitted grows in size, the difference between the size of the text and the size of the dictionary also grows, meaning this is a very effective method for compressing a large amount of text. Lempel-Ziff is one of the oldest, most simplistic and widespread compression algorithms out there. Its powers come from its simplicity, speed, and decent compression ratio. The algorithm is lossless, meaning it compresses data in such a way that allows for exact reconstruction of the original data. The algorithm forms the basis of many modern compression techniques like PNG, GIF, and zip file format. The general idea behind the Lempel-Ziff algorithm is to replace repeated occurrences of data with a single reference to a single copy of that data that has been already processed. There are several variants of the algorithm. The two most common are LZ77 and LZ78. The former one uses the sliding window approach. It works by scanning through the input data and searching for the longest match of the current data in a previously seen window, whereas the latter builds a dictionary dynamically and references this dictionary when repeated sequences are found. To get an idea of it, here is an example. Monkey see, monkey do, where monkey is a word that repeats later in the sentence. Thus, it can be replaced by a back reference token. Such a token consists of two numbers. The first one corresponds to how many characters it should look backwards, and the next one tells how many characters it should go forward and copy. All the mainstream compressors commonly used are some combinations of these techniques with different level of sophistication. Take the LZ4. a lossless data compression algorithm designed for fast compression and decompression, making it well suited for scenarios where speed is more critical than achieving maximum compression ratio. The algorithm is based on LZ77 with special optimizations to enhance speed. It uses the sliding window dictionary to find repeated sequences of data. When the match is found, LZ4 encodes as a pair, a distance from the current position to the match and the length of the match. In order to accelerate the search for matches within a sliding window, it uses a hash table. When a new sequence of bytes is encountered, it's hashed and checked if it has been seen recently. If a match is found, quickly LZ4 emits a token. Otherwise, it emits the bytes as literals. The algorithm is widely used in scenarios where speed is critical, such that real-time data compression, data streaming, embedded systems, or file compression. ZSTD is another efficient lossless data compression algorithm, designed as an alternative to the existing compression methods, offering better compression ratio and higher decompression speed. The algorithm is particularly well suited for scenarios where high compression ratio and low latency are required. The algorithm incorporates, similarly to LZ77, back references to previous data in the input stream to reduce redundancy, efficient for compressing repetitive data. Predefined dictionaries to compress small data blocks efficiently, particularly useful when data follows known formats or patterns. Advanced entropy coding that allows achieving higher maximum ratios while maintaining speed. Now, let's go back to the original problem. For many years, the only mode of compression available for internode traffic had been per message LZ4 compression. This is suboptimal because it fails to take advantage of substantial redundancy across messages. Hence, we chose to employ dictionary coding for still as RPC compression. The general idea is that some node in the cluster continuously samples its RPC traffic for some time and saves the sample to a file. When sampling finishes, a dictionary is trained over the sample, calling the ZSTD executable. A new dictionary is then distributed via Stilla tables. A dictionary trainer inserts a tuple, a timestamp, and a dictionary content into a table. When a new dictionary becomes available on both sides of the RPC connection, the connection switches to a new dictionary. Dictionary-based compression requires that both the sender and the receiver use the same dictionary. In particular, the sender can only start using a new dictionary after the receiver acquires it, and the receiver cannot forget a dictionary as long as the sender uses it. So they communicate via an ordered and reliable stream of messages, and the negotiation is performed for each node separately. We benchmarked various datasets to test internode compression with and without external dictionaries supplied. In all the cases, we can observe a significant gain in terms of compression ratios when dictionaries were provided. Furthermore, as long as data had some concrete structure, the ZSTD algorithm performed better than LZ4, reducing the size of compressed messages. Dictionary-based compression is now part of Stilla Enterprise. Thank you.